Hello, hello, hello. Hopefully everyone can see and hear me okay. Let's get that sorted. Welcome everybody who is here and who is has arrived for our revision session. Just going to sort my screen out. So let's see. Oh, there we go. We'll try that again. Oh, no. Again. Sorry, it disconnects itself. And it has no business doing. There we go. We've got the correct camera attached. Yes. Where did I get to? Hello. Welcome to our A-level chemistry revision session, Sunday sessions. Is it our first one of this year? I think it's the first one of this year for chemistry. We're going to be looking at calculating reacting masses, which is something that you learn about in year 12, but you need to be able to do all through your chemistry A-level. And this is incredibly important when you're looking at quite a few topics, actually, including some of the ones that you go on to look at in year 13. So it's a good one to be good at, if that makes sense, because it will help like your transition metals topic and redox and all of that sort of thing if you are good at doing calculating reacting masses questions. So hello, Moggerhead, nice to have you here. Please feel free to say hi in the chat. And if at any point throughout the session you have any questions, then do ask. And I will do my best to keep my eye on them, and then we can answer any questions. Or if somebody asks a question that you think you know the answer to, please feel free to answer them and we can chat about it. And I will be encouraging you to engage if you are able. So please feel free to pop your answers in the chat as well. And then you will get more out of it. The more you engage, the more you'll get out of these sessions. We'll get started in just a second, but we'll start off just doing a little bit of an intro about me. So welcome everybody, welcome back if you've been to these sessions before. We'll get started in just a second. So tiny bit about me. I am Alyssa, I'm the lead chemistry teacher at Snapprovise. I have a PGC in chemistry from Oxford, and I've been teaching A-level chemistry and tutoring and science and everything for ages now, for over 9 years, so loads of time. So objectives for this hour, or just less than an hour, we're going to look at recording the formula linking moles, concentration and volume. So that's something that you should have learned to GCSE, hopefully, but we're just going to make sure we're happy with it. We're going to look at performing calculations using moles, concentration and volumes. Again, something you've probably done a lot of, but if you haven't, this is a good practice, good time to practice. And we're going to look at performing calculations using mass and concentration as well. We're not going to look at ideal gases or ideal gas law. That we cover that in a different web class. So we're just going to be looking at these 3 objectives. So all of our web classes are aimed at any of the 3 main examples. I mean, technically, if you do any example at A-level chemistry, you will get something out of these web classes because a lot of the content is the same across the board. There's only tiny differences in what they expect from you. But if you are in AQA, OCR or EdXL, we also include your specification points, the specification points that are covered in these web classes. So these are the spec points if you are an AQA student. These are the spec points if you are OCR. Just bear in mind, we're not actually going to look at the ideal gas law today. And this is it if you are EdXL. Again, we're not going to be looking specifically at gases in this session. Okay, you have to excuse me, I'm slightly recovering from losing my voice. So I'll be making sure I drink lots. Right, so let's see how much we already know. So if you do know any of these answers, please pop them in the chat and have a go, because again, the more you put into the session, the more you'll get out of it. So the more you engage, the better you'll find this revision. But to begin with, do we know how to define a mole? Or what is the definition of a mole? When Avogadro came up with the definition of a mole, or defined this quantity, a mole, what did he say? What did he call it? Does anybody know? Please feel free to pop it in the chat. Or do you know how much, what the value of a mole is? So if I asked you for the amount of a mole, how would you define that amount? What would you say? This is one of the things that we do need to know. It's a bit of an abstract concept, especially when it's introduced to us at GCSE, if you do it at GCSE. If you don't do it at GCSE and it's introduced to at A level, it's still an oddly abstract concept. But all it is an amount. Oh, interesting. So that definition is often given for atoms, not moles. So it's not actually the smallest unit of anything, it's just a specific amount. So in the same way that when we say a dozen, we're talking about 12 of something, or when I say, I need a grand in cash, I'm talking about £1,000. We know that that means £1,000 because we're used to that meaning £1,000. A mole is an amount of substance in the same way that a grand is an amount of substance, or a dozen is an amount of substance, or a pair. We know that that means two. They're all names for amounts of substance. So a mole is the same, but the amount of substance is just a bit weirder than 12 or 2. A mole is the amount of substance with Avogadro's, sorry, not Avogadro's. And I should probably give him a capital, shouldn't I? Avogadro's number of particles. What is Avogadro's number? Avogadro's number is a specific number. It's the same across the board, but one of the examples, and I think it's OCR, but I'm not 100% sure, does ask for it to one more decimal place. But it's 6.022 times 10 to the power of 23. It's that many particles. So a mole is the amount of substance with Avogadro's number of particles, i.e., instead of us saying a dozen is 12 things, a mole is 6.02 times 10 to 23 things. Same concept. Okay, we also, when we're doing this topic, when you're doing anything that's to do with calculating masses, etc. Yes, well done, guys. Lovely, fabulous. Well done, Nightingale, as well. Lovely. When you're doing this topic, it's a good idea to get confident with your conversions. One of the conversions is decimeters cubed to centimeters cubed. How many centimeters cubed are there in a decimeter cube? How many centimeters cubed are there in a decimeter cube? Or if you would prefer, how do I convert between decimeters cubed and centimeters cubed? Now, I'm the kind of person who doesn't enjoy memorizing lots. So if I am lovely, well done. Anuj, very good. It is 1,000. If I am struggling to remember something, well done, Phoebe, as well. Brilliant. If I'm struggling to remember something, I will try and work it out. If I can't work it out, I will go back to basic principles to work it out. So 1 decimeter, deci meaning 10, so a tenth of a meter. A tenth of the meter in centimeters must be 10 centimeters because centimeter, hundredth of a meter. There are 100 centimeters in a meter. So a tenth of a meter would be 10 centimeters. So 1 decimeter must be 10 centimeters. But to go from decimeters to centimeters, we have just had to times by 10. To go from decimeters cubed to centimeters cubed, we have to times by 10 cubed, which is 1,000. So we end up timesing by 1,000 to go from decimeters cubed to centimeters cubed. So well done. Lovely if you got that. Brilliant. If that's already committed to memory, perfect. If it's not, either try to commit it to memory or go back to basic principles like I've just done there to work it out. Okay. What about decimeters to litres? How on earth do we convert from decimeters to litres? How many litres are there in 1 decimeter? Cubed. Sorry, 1 decimeter cubed. I should be specific. how many liters are there in 1 decimeter cubed? Again, we can go back to basic principles if we're not sure, if we don't know it off the top of my head, which often I don't, so I have to take it back to basic principles. I do know the conversion between milliliters and centimeters. So 1 milliliter is equal to 1 centimeter cubed, which means 1,000 milliliters is equal to 1 liter, or 1,000 centimeters cubed is equal to 1 liter. And since I've just done the conversion already, that 1 decimeter cubed is equal to 1,000 centimeters cubed, that must mean that my decimeter is also equal to 1 liter. So 1,000 centimeters cubed is equal to a liter. And 1 decimeter cubed is equal to 1,000 centimeters cubed. So 1 decimeter cubed must also be equal to a liter. It's good to be good at these conversions if you can. Finally, just to double check, do we know what the definition of molar mass is? What's the definition of molar mass? How would you define it? And it's an interesting point whilst you're typing, if you can come up with a definition, that molar mass is often what's meant when we talk about things like atomic mass, relative atomic mass, molecular mass, relative formula mass. Oftentimes, when we're just kind of teaching, when teachers are teaching, or when we're discussing things in general, we will say relative atomic mass or atomic mass, and actually we mean molar mass. Molar mass is much more of an umbrella term. It means we can use it with anything, because all it is the mass. So molar mass is the mass of 1 mole of something. 1 mole of a substance. So molar mass is the mass of 1 mole of something. That is the molar mass. And usually our mass is given in grams, so it's grams per mole is the unit. Okay, if anybody is not happy with any of that, then do drop a message in the comment. Otherwise, we're going to move swiftly forwards to see if we can get any of these questions done. So first of all, we're going to look at moles concentration and volume. Again, this might be, or hopefully will be revision to you. If it's not, don't worry. It's not much more difficult than GCSE. But we should know the relationship between moles concentration and volume. Now, lots of people have lots of different ways of remembering it. Lots of people remember N equals CV. So N being moles is equal to C, which is concentration, times volume. But we have to make sure, if we're doing it like this, that our concentration and volume are in the same units, or use the same units, which is not always the case. And they love to pop a unit conversion into these questions. So because concentration is usually given in moles per decimeter cubed, so mole dm to the minus 3, our volume must be given in decimeters cubed, otherwise we can't interconvert, otherwise we can't use them in this relationship because the units are wrong. So that often means our volume given in centimeters cubed needs to be divided by 1,000. So also lots of people like to remember moles equals conc times volume over 1,000, which I'm absolutely happy for you to remember, as long as you are aware that it's when the volume is in centimeters cubed that it must be divided by 1,000. If the volume is given in decimeters cubed, we don't have to convert it, so you don't need to divide by 1,000. If you're not comfortable, oops, I thought to put my mole units in there. If you're not comfortable with interconverting using an equation triangle, you don't have to. You can just rearrange using an equation. So use the N equals CV equation and rearrange it. But if you are, or you do enjoy using equation triangles, the one that's at the top, if I was looking for volume, then moles divided by concentration is equal to volume. If I was looking for concentration, moles divided by volume is equal to concentration. And if I'm looking for moles, then it's concentration times volume. And that's how our equation triangles work. The other way to do it, just as kind of to repeat almost what I've just said, is you can use the concentration units. If you know the concentration units, concentration is moles per dm cubed. Moles is moles. Dm cubed is a unit of volume, and it's per unit of volume, so it's got to be moles divided by volume. So hopefully that will help you to remember it. Feel free to jump ahead. Can you have a go answering this question? What would you give as your answer for this question on the right? So it says, calculate the number of moles of HCl in 50 centimeters cubed of a 5 mole per decimeter cube solution. Feel free to jump ahead and pop an answer in the chat, because we can see whether or not your method is correct. If it's wrong, we can work out where you went wrong. But otherwise, what would you do first? Maybe if you're not sure how to get there, think about what you would do first. The first thing that I've noticed is that we've got 50 centimeters cubed. So I'm trying to calculate the number of moles of HCl in 50 centimeters cubed of a 5 mole per decimeter cubed solution. I personally like to underline useful bits of information. That looks good. Well done. Well done, PKB. That looks good. I like to underline the useful bits of information, and if I need to, if it's a weird one, I often circulate. That's because I read the word calculate when I said that. Circle the keyword. Well done, Victoria, as well. Lovely. Let's just double check how we get there. But that's brilliant. Just to help remind you what we're doing. So, first of all, I've noticed that we've got 50 centimeters cubed in a 5 mole per decimeter cube solution. So I need to convert. 50 centimeters cubed to decimeters cubed. Oops, forgot my cubed bit. So I divide by 1,000 to get 0.05 decimeters cubed. Then I can just use my equation. I'm looking for the number of moles, which is equal to concentration times volume. I've converted my volume already, so I don't need to convert it twice. So it's just concentration times volume. The concentration I've been given is 5 moles per decimeter cubed, and I'm timesing it by the volume, which I've just converted. So 0.05 decimeters cubed. That gives me 5 divided by 0.05 is 0.25 moles. And just as a double check, I will hugely advocate for using units. If you're not a units person, I would get used to using them, because it's a really nice way to work out whether or not you've made any errors throughout a calculation, or maybe you've forgotten that maybe you've done C divided by V, perhaps, maybe you made a mistake. But you can notice, if we see here, we've got per decimeter cubed, so divided by decimeter cubed, and then we've got times by decimeter cubed. So times by decimeter cubed, divide by decimeter cubed means that they cancel. So the units we're left with is mole, and that's what we're looking for. So that works then. That makes sense to us. So we've hopefully, therefore, not made a mistake. And does 0.25 mole look like a good number? Does it look like it's a normal molar amount? Yes, it does. If I had like 48,000, I'd probably be thinking 48,000 moles. When do we usually do calculations about 48,000 moles? Not normally. So that's probably wrong. But 0.25 moles sounds reasonable. Awesome. Well done, those of you that got that. That's fabulous. Feel free again to go ahead and see if you can come up with these numbers first, or if you're not so confident, you can wait and then we'll talk through them together in a second. So the first question says, KCl reacts with a 3 mole per centimeter cube solution of AgNO3. Calculate the volume in decimeters cubed of silver nitrate solution needed to react with 10 moles of KCl. So I'm calculating a volume of silver nitrate that needs to react with 10 moles of KCl. How do I start with this? It's a little bit more different It's a little bit different to the one we've just done, because now I'm starting with so I've been given an amount of KCl, but I'm trying to find out an amount of silver nitrate, AgNO3. So I can't just use the moles of KCl straight away, because I haven't got moles of silver nitrate, I've got moles of KCl, so I can't just use the moles of KCl. What do I need to do? Even if it doesn't result in a change of a number, what do I need to recognize first with these reactions? I need to use the balanced equation. The balanced equation is basically like a recipe. For every one lot of KCl you have, one amount, you need another one lot of AgNO3. So that means they are in a ratio of 1 to 1. That means if I had 5 lots of KCl, I would need 5 lots of AgNO3. If I had 1,000 lots of KCl, I'd need 1,000 lots of AgNO3. How many lots do I have? I've got 10 moles of KCl. I've got 10 amounts. It's just like saying 10 dozen KCLs. I haven't. I've got 10 moles of KCl. So if I've got 10 moles of KCl, then because it's a 1-to-1 ratio, I'm also going to need 10 moles. Oops, didn't look like handwriting, did it? 10 mole of AgNO3, because it is a 1-to-1 ratio of KCl to AgNO3. That means I've now got a mole of AgNO3. I'm calculating the volume of it, and I've got a concentration. So there we go. I'm looking for the volume. That's what I'm looking for. My concentration, actually, let's write it over here. Volume is what I'm looking for. Concentration I've been given as 3 moles per centimeter cubed. And I've worked out my molar amounts are 10. Moles is 10. So I've got to up the 3 things that go in my equation. My equation is N equals CV, but I'm trying to find volume. Then I can rearrange by dividing by concentration to get volume is equal to moles divided by concentration. Now, personally, hopefully you would have noticed we've got moles in centimeters, sorry, concentration in centimeters cubed or per centimeter cubed, but the volume they've asked for in decimeters cubed, which is actually the opposite way around to what usually happens, but it's still a conversion that we need to do. So you could, if you wanted to, convert concentration to from moles per centimeter cubed into moles per decimeter cubed. But that conversion is harder to do or harder to get right. So what I would do, if it were me, is work out my volume in centimeters cubed and then convert it to decimeters cubed. So all I need to do is plug in my numbers to get volume. So moles is 10 mole. Concentration is 3 mole per centimeter cubed. I can see again, just after using units, I've got mole divided by mole per centimeter cubed. Cancel the moles. The per centimeter cubed is then going to be brought up because it's divided by per. So it's divided by, which means times. So 10 divided by 3, my volume is 3.3 centimeters cubed. So converted to decimeters cubed is centimeters cubed to decimeters cubed. Oh, I've got to divide by 1,000. Funny then. So 3.3, I think it's 3.3 recurring, times 10 to the minus 3 moles of AgNO3. I also, just as another aside, advocate for including labels where possible. Just because when you're in an exam, if you come back to a question because you're not 100% sure about it, or even with your examiner, when they're looking through your notes, if you just have random numbers written everywhere, if your random numbers aren't labeled and it's difficult for an examiner to follow your working, you won't be able to be given working marks. Even if actually what you've done is just copied a number incorrectly and made your way through the working out correctly, if you haven't labelled what you've done and an examiner can't easily see what you've done, you won't get the working marks. So I do highly recommend you label things. So you say, right, this is what I think is the amount of KCl. This is what I think is the amount of AgNO3. This is the concentration of this. This is the moles of this, etc. Just is a very good way of encouraging an examiner to give you working out marks. It makes it easier for them then to work out what you've done, and they can give you method marks. Okay, let's do the same thing for this one. Again, please feel free to jump ahead and come up with an answer if you feel able. But if not, what information have we been given? We have been given 0.35 moles of lead nitrate react with 100 centimeters cubed of HCl. Calculate the concentration of HCl. So we're calculating concentration in moles per decimeter cubed. We've been given a volume of HCl, but a molar amount of lead nitrate. Our equation is the same, N equals CV. Moles equals concentration times volume. I'm trying to calculate concentration, so I'm going to need moles and volume. I haven't got moles of HCl though, I've got moles of lead nitrate. So how do I get moles of HCl? Well, my moles of lead nitrate are 0.35. What's my ratio? Again, I've been given my balanced equation. It's a 1:2 ratio this time. So if I have one lot of lead nitrate, I need twice as much hydrochloric acid. So in this case, I've got PbNO3 2 HCl. This is a 1:2 ratio. I've been told I've got 0.35 moles of lead nitrate. So how much HCl do I need? I should need twice as much, so 7 moles. Oh, sorry, 0.7 moles. I forgot my decimal place. 0.7 moles, oh geez. So my moles of HCl are twice the moles of lead nitrate, but they are 0.7 mole. Then I can just plug some numbers in. Let's just double check our units. So I've got 100 centimeters cubed of HCl. So if I work out my volume of HCl, if I do a conversion, I'm going to do the conversion before I plug it into the equation, but you're more than welcome to do it during the equation. It's a bit easier then, or quicker anyway, on your calculator. So my volume of HCl is 100 centimeters cubed, which in decimeters cubed divided by 1,000 is 0.1 decimeters cubed. So then I'm trying to calculate concentration. Concentration is equal to moles over volume, moles divided by volume, as long as our units are the same. My moles are worked out as 0.7 moles. My volume, I've just converted it to get it into decimeters cubed. So it's 0.1 decimeters cubed. Oops. So 0.7 divided by 0.1 gives me 7 moles per decimeter cubed of HCl. If anyone's not happy with that, then let me know. But one of the things that we encourage you to do is to just take a minute to kind of, or not even a minute, 10 seconds to think about how confident you're feeling about your learning about that. Is that something that you think you followed? So you understand it, but actually maybe it's not something you feel confident of doing yourself. Is it something that actually you feel very confident with? So, yep, quite happy, but found that quite straightforward. Or is it something that actually I didn't even follow that? I've got no idea what some of these terms mean, and I really need to go back and kind of revise from scratch. Because if you do this, if you take the time to go through it every now and again, quickly, just quick little check-ins, you will learn where you feel confident, where you don't. And also, if you feel confident about something when you're doing it, and then you go to do an exam question and actually you get it all wrong, then that tells you that you need to think about how you're revising and how you're learning, because perhaps you're not revising soon enough after doing a topic to keep it fresh in your head. So it's a good way, kind of, it helps you to learn It can help you to develop, your revision, your learning methods. Lovely, thank you, Akana, for letting me know. If anybody else wants to let me know how you're feeling, please do. You don't have to. It's just a good way for me to know how you're doing, but also for you guys to reflect. So fabulous. Let's have a go at this exam question. This is a nasty exam question, so we're going to go through it nice and speedily if we can. But hopefully making sure that we include all the steps. So there's a lot going on here, so you have to bear with me. Again, if you want to skip ahead and come up with any of the answers, please do and pop them in the chat. I would encourage you to, because it gets you engaged and keeps you motivated, and your engagement means you're more likely to be learning, but you don't have to, of course. Okay, so there's a lot of information here, so I'm going to read through it, but please feel free to mute me and read it yourself if my voice is confusing you. But I'm also going to highlight any bits of information that I find which I think might be useful. They might not be, but I'm going to highlight or underline even things I think are going to be useful. So a student was given 200 centimeters cubed of solution X oxide, NaOH, and so hydrogen carbonate have both been dissolved. It's always a good idea to notice what words they have bolded, what words they put in bold in an exam question, because as an inside tip, that is usually where students have made errors in the past. Okay, so just bear that in mind. So always a good idea just to kind of double check what words they put in bold, because that's helping you to not make a mistake, and it's encouraging you to think in the right direction as well. So they've both been dissolved. The student carries out 2 different titrations on samples of solution X using 1 mole per decimeter cubed of sulfuric acid. In the first, both the sodium compounds were neutralized. In the second titration, only sodium hydroxide was neutralized. The student's results for the titrations, oops, where's my video just disappeared? Sorry, my video just disappeared. I must have knocked the camera thing again. Go back. There we go. Where do we get to? The student's results for the titrations of a 25 centimeter cubed sample of solution X are shown. The volume of sulfuric acid needed to neutralize both of them was 2950. The volume of sulfuric acid needed to neutralize only sodium hydroxide was 18. Then we've been given the reacting ratios, so we've been given the balanced equations. And then it says, calculate the amount in moles, so that's what we're calculating, of H2SO4 used to neutralize only the sodium hydroxide in 25 centimeters cubed of solution X. How do I do this? What numbers do I need to use? I'm trying to calculate the amount, so the moles of sulfuric acid used to neutralize only sodium hydroxide. What are we looking at? Well, we actually have a titration that was used for only sodium hydroxide, and that gives us a volume of sodium hydroxide. Sorry, a volume of sulfuric acid even. We want to know moles of sulfuric acid. So if we think, what calculation are we likely to be doing here? Well, if we use our N equals CV, moles equals concentration times volume, I've got moles is what I'm trying to calculate. I've been given a volume of sulfuric acid, so all I need is a concentration, and I've been given one to calculate moles. Moles equals conc times volume, as long as the volume is in deciliters cubed. Here they've given it to me in centimeters cubed, so because we've done it twice before now, I'm going to do it within the calculation. So N equals CV V over 1,000 when my volume is in. So 0.1 mole per decimeter cubed is my concentration that I was given. Times the volume, which is 18, but it's in centimeters cubed, so I'm going to divide by 1,000 cubed. That gives me 1.8 times 10 to the minus 3 moles. times 10 to the minus moles. That's all I need to do for that one, because all it wants to know is the amount, the moles of sulfuric acid needed to neutralize sodium hydroxide, which is what that bottom second titration is on about. So that's fine. It then says calculate the concentration solution X. So now we want to calculate the concentration of sodium hydroxide. Now, those of you that have done lots of titration calculations, you might be confident at working this one out. One of the key aspects of titrations is that it has our molar, it shows a molar equivalent. At the point of a titration, or the point at the end point of a titration, species. And not the correct ratio of moles. So I know how many moles of H2SO4 were used in that titration to get to the end point. So how many moles of sodium hydroxide does that mean was in my solution? Well, if we look back at our what they're called balanced equations, we can see there's a ratio 2:1. As in, for every 1 mole of sulfuric acid, we need twice as many moles of sodium hydroxide. Sodium hydroxide are twice the moles of sulfuric acid. Mole hydroxide are twice the moles of H2SO4 because it's a 2:1 ratio, 2 lots of sodium hydroxide sulfuric acid. So I'm trying to work out my moles of sodium hydroxide, I've got to double my moles of sulfuric acid. That means that moles is 2 times 1.8 times 10 to the minus 3, whatever that is, 3.6. I don't want the moles. I want the concentration. Oh, my chat has just disconnected itself. Let's see what that means. Okay, we're back in. That's fine. Apologies, guys. It just said my chat disconnected. So apologies if you've just briefly missed that. We've just worked out using moles of H2SO4, noticing that there is a 2:1 ratio in the balanced equation. So we need twice the moles of H2SO4. So we've got 3.6 times 10 to the minus 3 moles, but they want concentration. Concentration, if we look at N equals CV, is equal to moles divided by volume. I've got the moles, 6 times 10 to the minus 3 mole. What about what volume do I need to use? I've got a volume of 25 centimeters cubed. Because it's in centimeters cubed, I need to convert to decimeters cubed. 25 over 1,000 to convert to decimeters cubed. And that gives me 0.144. It's just said it disconnected me again. Oh no, I'm back. For some reason, my chat just disconnected itself again. It's not done this before. This is interesting. Please let me know if you can no longer hear me or anything, because it might be that my, laptop's playing up or something. Hopefully it's not. Let's keep going. If anybody's not happy with then otherwise we're going to keep going. So part BI says calculate the amount in moles. So calculate the amount of NaHCO3. So we've got a couple of things we need to do here. First of all, if you're ever unsure when you come to these questions about what to do, see if you can work out the number of moles of something. Okay, That's what we did with part 2. When we come to BI, sorry, A2 that was, about how we can work out the number of moles. Now it's asked for the number of moles of sodium hydroxide, sorry, of sodium hydrogen carbonate, but we haven't got a number that's just sodium hydrogen carbonate. We've got a number, we've got a volume, a titration titra value for sodium hydroxide and sodium hydrogen carbonate. So how can we use that to work out the moles of just sodium hydrogen carbonate? Well, if you look at it, we know that 18 of those 29.5 centimeters cubed, 18 of those were used to neutralize just or only the sodium hydroxide, the NaOH. So the rest of it must be what was needed to neutralize the sodium hydrogen carbonate. So my volume volume of H2SO4 needed to neutralize sodium hydrogen carbonate must be 29.5, the difference between 29.5 and 18, which is 11.5, I believe, centimeters cubed. Now I've got a volume. Let's just quickly convert it to decimeters cubed, because I know I'm going to need to use decimeters cubed, because all of my concentrations are in decimeters cubed. So divide by 1,000 gives me 0.0115 decimeters cubed. Now, how can I use that to work out my amount of sodium hydrogen carbonate? Well, I've got a volume of sulfuric acid. I can work out my moles of sulfuric acid because I know I've got my concentration of sulfuric acid and I've got a volume, so I can work out moles. So H2SO4, sulfuric acid, moles equals conc times volume. So my concentration I have from earlier is 0.1, that was given to me in the question. Decimeters, moles per decimeter cubed, times by the volume, which I've just calculated as 0.0115 decimeters cubed. That gives me 1.15 times 10 to the minus 3 moles of sulfuric acid. How do I go from sulfuric acid, moles, to moles of sodium hydrogen carbonate? But again, I need to look at my reacting ratios. I need to look at my recipe. What do I need? How do they react? How do they interact? Well, again, it's a 2-to-1 ratio. 2 lots of sodium hydrogen carbonate to 1 lot of sulfuric acid. So that means if I've got 1.15 times 10 to the minus 3 moles of sulfuric acid, I'm going to need twice as much for my moles of sodium hydrogen carbonate. So my moles of sodium hydrogen carbonate is 2 lots of the moles of H2SO4, which is 2 times 2 times 1.15 times 10 to the minus 3, which is my moles of sodium hydrogen carbonate is 2.3 10 to the minus 3. But that is in 25 centimeters cubed, because that's in our titration value amount. They've asked for 200 centimeters cubed, not 25 centimeters cubed. So how do I go from the amount of moles in 25 centimeters cubed to the amount of moles in 200 centimeters cubed? Well, I'm going to need to work out my conversion. How do I get from 25 centimeters cubed to 200 centimeters cubed? That is 8 times bigger. So if I times my moles sodium hydrogen carbonate in 25 centimeters cubed by 8, I will get the number of moles in 200 centimeters cubed, which is 0.0184 moles. So a lot of work for 2 marks, that is mean. That's what that question is. Mean. Go. Oops. I think we're all back again. So yes, please do let me know if you have any questions. Otherwise, we're going to move swiftly on to the next section. We've got another 15 mins. We'll have a go at this. So we're going to have a look at calculations using masses. These ones is basically the same thing. It's just we're using a different equation. So calculations with mass. Often calculations are done given mass rather than moles. Now you might be more used to see use mass rather than moles because moles is be given calculations using masses. The process is the same. We just might have different such as we know that we've got moles equals concentration times volume, but we can also use equation, which is mass is equal to moles times the molar mass. So often calculations are done given mass rather than moles. So let's have a look at this one here. 100 grams of lithium nitrate reacts with 300 centimeters cubed of ammonium nitrate. Calculate the concentration of ammonium nitrate in moles per decimeter cubed to 3 significant figures. Let's have a look. We know that mass is equal to the number of moles times the molar mass of that thing. We've got 100 grams of lithium nitrate. So if we wanted to work out the number of moles of lithium nitrate, lithium nitrate, maybe I need to say, that's equal to mass divided by mR. The mR of lithium nitrate, well, I haven't been given it, but I can calculate it, and I won't do it now because otherwise we'll run out of time. But mR, molar mass, in this case, I'm actually calculating the formula mass because I want to know the formula of the mass of one lot of Li3N. But if I do the quick calculation, I should get 34.7 grams per mole. Always use the numbers that you're given in on your periodic table. So just double check that you use those numbers rather than any numbers that you memorize, unless you want to memorize your periodic table. But so the molar mass of lithium nitrate is 34.7 grams per mole. So I know the mass because I was given it earlier. It's 100 grams divided by the mR, which I've just calculated, is 34.7. Again, I can see units-wise, I've got grams divided by grams per mole. The grams are going to cancel the grams. The per mole, because it's divided by per mole, is going to move up to the top to just be mole. So I end up with 2.888 moles. My units have worked out to be moles, and that's what I'm trying to calculate. So that means probably I've got it right. So that's my moles of lithium nitrate. They want to know the concentration of ammonium nitrate. Well, now I need to look at a ratio then. I've got 1 mole of lithium nitrate to every 3 moles of ammonia. That means I need 3 lots more, 3 times as many moles of ammonium nitrate as I have lithium nitride. I've realised I might have been saying nitrate for lithium nitrate, and I should have been saying nitride. So well done if you picked that up. Apologies. That should be nitride. That's just me being lazy. Should be lithium nitride, Li3N, not nitrate. So 3 lots of ammonium nitrate to every 1 lot of lithium nitride. So because it's a 1 to 3 ratio, I'm going to need 3 times as many moles of ammonium nitrate. So if I'm trying to calculate my moles of ammonium nitrate, oops, NH4NO3, it's 3 lots of my moles of lithium nitride, so 3 lots, which comes out at 8.64 moles. I'm still looking for the concentration of ammonium nitrate. I've now got the moles and I've got a volume because I was given it in the question. So now it just becomes my moles const volume equation. So concentration is equal to moles divided by volume, which is 8.64 moles divided by volume, which is in centimeters cubed, but I need it in decimeters cubed because that's what my concentration is. So it would be 300 centimeters cubed, but divided by 1,000 to put it into decimeters cubed. And that comes out at 28.8 mole per decimeter cubed, just 3 significant figures, because that's what I was asked for in the question. If anyone's not happy, drop a line in the chat, but we'll keep going because I want to try and make sure we can get through everything. So that's our answer to that one. The next question says, we have 0.8 mole per decimeter cubed sodium carbonate. It reacts with 12 grams of potassium fluoride. Calculate the reacting volume of sodium carbonate. So I'm looking for a volume of sodium carbonate. I've been given a concentration. So if I want to work out the volume, I'm going to need moles of sodium carbonate. But I haven't been given moles of sodium carbonate or even a mass of sodium carbonate. I've been given a mass of potassium fluoride. But I also have my reacting ratios. So I know that 1 lot of sodium carbonate reacts with 2 lots of potassium fluoride. So if I work out how much potassium fluoride I've got, I also know how much sodium carbonate I had used. So my mass of potassium fluoride is 12 grams. The moles of potassium fluoride, therefore, is mass over MR. Well, I don't have the MR yet, so let's work that out. The MR of potassium fluoride is 58.1 grams per mole. So I've got 12 grams divided by 58.1 grams per mole. That means my moles of potassium fluoride are 0.206 moles of KF. But I don't want moles of KF, I want moles of sodium carbonate. Now in this case, I've got 2 moles of KF to every 1 mole of potassium carbonate. So I need half as many moles of sodium carbonate. So I actually need to halve my moles of potassium fluoride to get my moles of sodium carbonate. Moles of NaCO3 are my moles of potassium fluoride divided by 2. So 0.206 moles divided by 2, which is 0.103 moles. That's the moles of sodium carbonate. But I don't want moles of sodium carbonate, I want volume of sodium carbonate, but I've got a concentration, so moles divided by concentration. My moles are 0.103. My concentration is 0.8 moles per decimeter cubed. That's going to give me a volume in decimeters cubed. Doesn't matter though. So volume of NaCO3, which is 0. Decimeters cubed, again to 3 significant figures. Oops, sorry, didn't mean to do that. So that's to 3 significant figures. Anybody got any questions? Anybody not happy? Okay. Let's have a go at some exam questions. Again, worth just having a quick check. Just have a think. Are you following? Are you happy? Is there something that you might need to practice? Is it something that's going completely over your head and you're really struggling with? In which case, go back to basic principles. Try and understand what a mole is and how those numbers are related. But in the meantime, let's see if we can finish off with a super quick exam question. I'm going to need to speed through this one because we have only got a couple of minutes left. So again, feel free to turn off the sound if you want to just read it through yourself, but I'll just read through the question really quickly and then we'll get on with answering it. So calcium phosphate reacts with aqueous nitric acid to produce phosphoric acid and calcium nitrate as shown in the equation. Blah, 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 blah. A 7.26 gram sample of calcium phosphate reacted completely when added to an excess of aqueous nitric acid to form 30 cubes of solution. Calculate the concentration in moles per decimeter cubed of phosphoric acid in this solution. Give your answer to 3 significant figures. So I've got an amount of calcium phosphate and it wants the concentration of phosphoric acid that's produced. So I've got an amount of calcium phosphate. I'm looking to find the amount of phosphoric acid. Well, first of all, let's see if we can work out the number of moles of something. What have we got? We've got a mass of calcium phosphate. Well, again, we know that mass equals NMR. So the mass of something is equal to the number of moles times its molar mass. So if I work out the molar mass of calcium phosphate, Ca3PO42, I can work out the mass of it. Sorry, I can work out the moles of it. So that's the MR is 310.3 grams per mole. Therefore, the moles of calcium phosphate, if I rearrange my mass equals NMR equation, moles are equal to mass divided by MR. My mass I was given as 7.26 divided by the MR, which is 310. I've just worked it out super quickly. Again, I would normally leave you time to do this, but we are short on time. There's a lot to do in this equation, in this class. So that would end up being 0.0234 moles of calcium phosphate. Now they want to know the concentration, of phosphoric acid. So in order to know concentration of phosphoric acid, I need to know moles and volume of phosphoric acid. Well, I've been given a volume, but I don't yet know the moles. So how do I work out the moles? Well, let's look at the reacting ratios. It's 1 lot of calcium phosphate to every 2 lots of phosphoric acid. So again, I'm going to need twice as much. So my moles of phosphoric acid, H3PO4, are equal to 0.0234 the moles of calcium phosphate times by 2, because I need twice as much, which is 0.0467 moles. Now I've got moles, been given a volume already earlier in the question. So my concentration, so N equals CV. Concentration, if I rearrange that, is equal to moles divided by a volume, as long as they are in corresponding units. My moles are 0.0467. I just calculated that. That's my concentration of phosphoric acid, sorry. My moles are 0.0467. My volume is 38 centimeters cubed, so I need to convert to decimeters cubed. So divide by 1,000 to convert to decimeters cubed. Means my concentration of phosphoric acid is 1.23 moles per decimeter cubed, or 5 moles. See, that 5 marks is lovely for that amount of calculations. In the previous question we did, where it was only 2 marks for a lot of working out, that was it. It all depends, the marks change depending on what else is in the exam. So in this exam, there's probably very little moles questions, so they've given us lots of marks for them. In the other one, there's probably lots of moles questions, so there are already marks available for the, easier bits or for the interconversions, etc. Okay, so we should be able to recall the formula linking moles concentration and volume, N equals CV, perform calculations using moles concentration and volume, and perform calculations using mass and concentration as well. Our mass equation being mass equals NMR. Mass equals moles times molar mass. Before we disappear, does anyone have any questions? Please do feel free to check out the, oh, sorry, I pressed my video button again. Please do feel free to check out the YouTube class, the YouTube schedule, sorry, to see when there are any upcoming YouTube classes. They should be on the schedule, or at least the ones that we've scheduled in should be in there. And I hope to see you at a future session. Thank you very much and well done if you've managed to make it to the end. Please feel free to download the slides to go through this again in the future if you want, and go and look at the back catalogue as well to see any older web classes. Thank you very much. See you very soon. Bye.